Wrong link. I'm Venkat, I'm Professor Bauman's graduate student, and I'll be covering this lecture today. So we are in chapter 10, we're learning about general Markov random fields. And so far what we have really looked at is we've defined an MRF, what is a Markov random field. We've defined a Gibbs distribution and shown that how they're related by the Hammersley-Clifford theorem. Then in the next segment we looked at 1D MRFs and 1D Markov chains and showed that they were equivalent. In the next segment we moved on to the ising model, and that's where we kind of ended. So in today's lecture I'll just quickly go over what we learned about the ising model, and then we start the next section of chapter 10. So let me just move to the document camera. Okay, so last time when we left, we looked at this model called the ising model. So it was a model, it was developed in order to explain the behavior of certain materials, which when cooled, all of a sudden they got magnetized. So in order to explain that behavior, they came up with this model, where the probability mass function is given by this expression, and the bottom line is it's a function of, the difference between vertical and horizontal neighbors. And what this type of density function, which is parameterized by beta, helps to explain that behavior. And I'll just quickly go over the 2 or 3 key results that we looked at last time. First result that we looked at was this. So given that type of ising model, the conditional probability of a pixel being 1 given every other pixel was only a function of the neighbors. And the point was, for these values of beta being large, it basically penalized neighbors being different. So when beta was large, it encouraged a pixel to be the same value as its neighbor. And that was given by this graph over here, where we saw that as the values of beta went up, and as the number of neighbors that were equal, which were equal to 1 went down, the probability of that pixel being 1 goes down. So that was one result we saw. Another very cool result we saw was that the probability, so if you have an ising model on a 2D lattice, and as the lattice size goes to infinity, the probability of a center pixel being equal to -1, given the boundaries were 1, is strictly bounded away from half. And in fact, you can make the probability of that pixel go almost to 0 by making beta sufficiently large. So that's the whole point. The point was, as we increase the beta, we're kind of increasing the correlation in the field. And that, and furthermore, as I said, it is an abrupt, the critical observation is that there's an abrupt change. So on Saga, if we in fact derived a closed form expression for the conditional expectation of a pixel given the boundaries are equal to 1 by this expression. And we will look at it now quickly. So what this really tells us is that, roughly speaking, as the value of beta becomes really large, the expected value of the center pixel being equal to 1 is very high. So it's very high, there's a very good chance that the center pixel is equal to 1 given that the boundaries are pixels are equal to 1. And what does it mean if a pixel can take on just 2 values? So remember, we're talking about a material that can take on 2 values, plus and minus 1. If the expected value of that variable is equal to 1, what do you know about the probability of that? What is the probability distribution? So, right. So if a random variable takes on 2 values, plus and minus 1, and you know that the expected value is equal to plus 1, it means the probability of being minus 1 is very close. And similarly, when the value of beta is below critical temperature, then the expected value of the pixel is equal to 0, which means that both states are equally probable. And what we saw last time was that beta is inversely related to the physical temperature. So what that means is that as beta is small, means the temperature is very high, and that means there are no correlations in the field. But as beta becomes large, it means the temperature is being cooled, and it starts to introduce correlations in the field. So that was a big result. So they basically were able to explain a physical phenomenon by a probability distribution, or other family of distributions parameterized by data. And when we do the analysis for this, it explains that exact phenomenon. So the point is, unlike in a Markov chain, there are correlations between the boundary and a pixel which is far away from the boundary. So that's one of the big, I guess, take-home messages from analyzing this ising model. So there's one little segment which I'll just quickly go over, so one of that we can basically generalize this ising model. So but when we generalize it, so the ising model we had, like each random variable could take on plus or minus 1. Instead, we can generalize it to have m levels. And when we have m levels, and we have a random field, each random variable can take on m levels, then it's we can no longer get nice closed form expressions for the property. But nevertheless, it's a very important model. So can you think about, can anyone here tell me a reason why we're looking at m level models? What kind of significance, what application, image processing can we look at?
For example, like image might be 36 pixels, or images aren't just one point, one white hole.
Yeah, that's good. So that's it. So basically, you can have this. One of the big applications that comes up is segmentation. So MRFs, these type of MRFs are useful when we do segmentation. So in segmentation, the model is each pixel belongs to one of n classes. That's why m level m level models are important. And you can go through this. So we can basically once again write the distribution function, or the mass function for this is given by, similar to what you saw in the ising model, where you have, instead of, and here we have an 8-point neighborhood, so you have two parameters, beta 1 and beta 2, which penalize differences between either horizontal vertical neighbors or the diagonal neighbors. So here's the point. I think the big point here is that beta 1 and beta 2 control, they discourage differences, they penalize differences between neighbors. Okay, but from the image processing perspective, that's like the utility of these parameters. So one thing you can go ahead and do is you can then go and maybe just zoom in. So the point that you can write down the mass function, and then you can also write out the conditional density from of a pixel given all the other pixels, and it only depend on a neighborhood. So the reason this expression is being given over here is that, again, when you use it as a model for images and do some kind of optimization, some kind of estimation, you often require to compute this term. So what here is, this is a formal expression for that in the case of an n-level discrete Markov random space, ising model. So with that was just like a review of what we did last time. Okay, so today what we're going to do is look at 2D Markov chains and MRF. So we learned about the ising model, we learned about its significance. Now the question is, do we even need to go okay. So the question then is, I guess the question is, we've looked at the ising model, and we know the ising model has a Gibbs distribution, and therefore it's a Markov random field. So the question for today's class is, I guess in some way, are Markov random fields and Markov chains equivalent in 2D? So do we even need Markov random field theory, or can we just have a theory of 2D Markov chains and explain and use it as an effective model in 2? And the answer to that is, in 2D that's not true. And so what we're going to do next is to see why that's not true, and in which we're going to basically kind of make that idea very clear. So the first thing we need to do before we jump into this is to really define what is a 2D Markov chain. Right? In 1D we know what a 1D Markov chain is. We've seen that, we've done a lot of analysis. So we need to first go ahead and define it. So in order to do that, the intuitive kind of explanation for what it is, what a 2D Markov chain is that the conditional probability of a pixel given all the past pixels. So the conditional probability that a center pixel is equal to something given you have all the other pixels prior to it. So you need to define some notion of causality, right? So zoom out a little bit here. So you need to define some notion of causality, and the conditional probability of a pixel given all the past pixels only depends on a neighborhood, on a causal neighborhood. So it could be like for a p is equal to 2k, what you can have is you can have some type of a causal neighborhood like this. So this is the center pixel and this is like a causal neighborhood for it. So basically, if you just go ahead and write it down, the probability of this is simply equal to the probability of the pixel given S minus R, where R belongs to some window. And this is the type of window you saw earlier as well when you looked at AR processes and Gaussian GMRFs. Right? So you have to define some notion of causality. In a 2D lattice, this is one way to define it. So this is, I guess, this is an example of a causal neighborhood. So defining a 2D Markov chain, and so basically, the probability is given by this. So where WP is a window, this window that I've drawn over here. So, given that definition of a 2D MRF or 2D Markov chain, I guess so the question we're trying to answer is, I guess, is a 2D Markov chain equal to a 2D MRF? That's the question we're trying to answer. Having given a definition for it, it's basically a field order Markov chain was, basically just dependent on a window. The question is it equal to an MRF? And the answer to this is yes. So I guess, and we're going to next look at why is this true. So in order to go through the calculation, what you really need to do is to write down the mass function of the Markov chain. Remember, we have conditional the conditional densities. So what is the probability mass function of the Markov chain given the conditional density? For a Markov chain, how can we find the probability mass function of the field?
Initial state times the transition probability.
Exactly, that's good. So basically what you need to do is just take XS, given some neighborhood, which is a transition probability, and your S just belongs to the set of all lattice points, right? So in a Markov chain, if you have the freedom to write this. So given that this is true, alright, so given that we can write out the density function this way, we can then go ahead and formally write this in terms of the window that we're looking at. We're looking at a causal neighborhood or window of order p. So we can then go ahead and just write this as the probability of certain pixel x of s. So in this case, we define the neighborhood to be a pixel and then a window next to it. So you have xs minus wp. Alright, so what we're doing is, so we write that, and the next trick we do, remember we're trying to check if it's equal to an MRF, right? So we write out, and this is of course same as just writing you can just write this as the sum of the logs. So you can take the sum of the logs of right? This is fine. So basically, I'm just taking the exponent of a log. I've not really done anything. And why are we doing this? What are we heading to? What do you think? What kind of distributions have this kind of form?
Trying to characterize it gives.
Okay, that's correct. That's exactly what we're trying to do. So if I just now write it this way, So if I write little s belongs to s, sorry, and if I define some kind of potential function with like this, so what we've done essentially is started with the Markov chain and we've written it in terms of a Gibbs distribution, right? Okay, so what do we know of, so if this has a Gibbs distribution, and what do we know about, if we know it's a Gibbs distribution, what can we say next?
It's an MRF.
Exactly. So if we know that it's a Gibbs distribution, we know it's an MRF, right? And the potential function can be defined appropriately. Just going from here to here, I hope you can see that it's just, we could just see what the term over here. So the big picture is that, so it's a Gibbs distribution, and what are the, remember the clique structure over here. If you just take an example of P is equal to 2D Markov chain, which is what we looked at, this is the structure of the clique. Alright? So the Gibbs distribution, remember, you have a Markov chain, you have a Gibbs distribution, it's defined on a set of cliques, right? The clique for this case, for this 2D Markov chain we started, is of this form. This is the center pixel and these are all the other pixels in the clique. This is a single clique. Okay. Sorry for that. Let me know if I'm not, zoom out a little bit. So for the Markov chain, this is the clique structure. So given this is the clique structure, we need to find for the MRF what is the neighborhood structure, right? So in order to do that, let's just think about, so I think so this is something that you got to kind of understand how to do. So given a clique, so we know how the clique structure is. And I'm just drawing a lot of points in the field. And let's just say I have a pixel here. So in order to find the neighborhood system for this Markov random field, what we need to do is to find out how do we know two pixels are neighbors. Given a system of cliques, given the clique structure that we just looked at, how do we know that if two pixels are neighbors or not? So I guess the question is, how do I know that is this pixel neighbor of the center pixel?
No, because they're not, depending on how you define your clique system.
So the clique system is defined in this way, right? The cliques are defined this way. So I guess the main question I'm trying to ask is, given the system of cliques, how do you know which are the neighbors of a center of a given pixel?
So as you define there, you can't be in like the following row. You have to be in either a previous row or like the same row or the previous column. Now, the way you just defined it. Now, generally, you have to be either like one across or like one away, like diagonal neighbor, or one away horizontal, vertical, and then like you have to be conditionally dependent on one another to be within.
That's partly true. Now, I think the more formal way that is good. I think the formal way of looking at it is that given a clique structure, two pixels are neighbors if they share a clique. So if you draw a clique with both the pixels, containing them, you can do that. So basically, so I can find a clique over here which with that structure, which contains both the pixels. So these two are neighbors. So similarly, you can go ahead and find out, so I'm just going to quickly just show what is the resulting neighborhood system resulting from that system of cliques. And the point is, you get a system like this. And for any pixel, any two pixels here, I can find that they share a clique. So this is the clique structure on the left, and I can always find 3, 4, 5. So I can find a clique that both these pixels are they share. So that's why these are not. So similarly, you can just you can draw these around and you can kind of verify what I'm saying. So that's the trick so that this pixel and that pixel are neighbors. All right, and you can go ahead and do this for everything, and you find out that when you're over here, you cannot find a click structure that these two are neighbors, that these two share, and therefore they're not. So that's just a little thing, but it turns out that if you want to really another more systematic way of going from here, from the click structure to the neighborhood, is to just take the 2D autocorrelation step. This is essentially what I'm doing. If you think about it, I'm just moving this thing around. All right. So where we started out is we looked at we defined we found the corresponding neighborhood system. So once we have done that, what it really tells us is that I'm sorry, let me just put this back up again for a second. So this was a P is equal to second order click corresponding to the Markov chain, and here you have you can get the number of neighbors kind of became 4. If you just look along this direction, 1, 2, 3, 4. This is the center pixel, and there are 4 neighbors, right? So what it kind of tells us is that a Markov chain, a 2D Markov chain of order P, kind of leads to a 2D MRF of order 2P. Though we really haven't defined the 2D MRF, that's where it's kind of going. All right. So given that, we can then go ahead next and define what a 2D MRF is, right? So basically for a 2D Markov random field of order P, if we consider a neighborhood system, define simply that the neighborhood of a single pixel, so a natural definition is for a P is equal to 1, then the order of the MRF is 1, this is the kind of neighborhood system that I get. This is a center pixel, so that's what the equation over here essentially leads to that. So P is equal to 1 here. Alright, so if we define the neighborhood this way, then the definition of a 2D Markov random field of order P is that the probability of a pixel given all the other pixels in the field is simply dependent on that neighborhood. Alright, so we defined a Markov chain and a 2D Markov chain of order P, and now we have defined a 2D Markov random field of order P. Alright, and the other thing we made a note of is that the 2D Markov chain resulted in a 2D MRF, but it's kind of doubled the order. Alright? Are there any questions about this? Okay. Alright, so with that definition, so I guess when I started, so the point is we're trying to establish if 2D Markov chains are equivalent to 2D MRF. And in that direction, we have shown that 2D Markov chains of order P resulted in 2D MRFs of order 2P. Is the other direction true? So if I have a 2D Markov random field, is it equivalent to a 2D Markov chain? Because if this was true, then we really wouldn't need to talk much about 2D MRF. So the answer to this is no. And the way we're going to show that is that we're going to just give a counter example, right? We just want to show that this is not true. We're going to go and look at a counter example. So can you give an example of a Markov random field that we've been looking at? What is the model that we looked at last time? But, so we looked at the ising model, right? So in fact, we're going to take the case of the 2D ising model and check and show that it's not a Markov chain. It's not a 2D Markov chain of order P. So what is the order of the 2D ising model? What is with the 4-point neighborhood? What type of an MRF is it? What order?
Order 1, right?
So that's correct. That's correct. So we're going to look at that and we're going to check if that results in a Markov chain. So if you go ahead and write, so in order to check if something is a Markov chain, how would you do it? The way you would do it is you would check if the probability of a single pixel, given all the pixels prior to it, is only dependent on a piece order window, a piece order causal window in 2D, right? So if you write out that expression, let me zoom in, right? So what we're trying to check is this simply going to be dependent on a causal neighbor. So when you write out this is just the joint density divided by just marginalize it over n, right? So this I think is pretty straightforward step. So now what you really need to do is, in order to evaluate the expression in the numerator, we need to take the joint density and sum it up over all the states that come after it. And I'll just show a picture of this quickly. So what we're trying to show here is, what is the probability of xs is equal to xs and xr is equal to xr for r less than n. So this is what we're trying to find out, and this is the same as the probability of xs is equal to xs, xr is equal to xr for r less than s, and k is equal to xk for k greater than s. Right? Your center pixel, the pixels prior to it, and the pixels after it, and you're going to, of course, sum this over xk. Right? So you're going to sum it over all the xk. So basically, if you had a neighborhood like this, and these are the other pixels, this is of course the set R, this is the center pixel S, and this is everything else. So you got to sum it over all the possible values of, these are the pixels prior, this is the set R, this is the center pixel S, and this is everything that is beyond S. So you got to sum it up over all possible values of this set. So if each of this could be binary, it can take on you get these several sets. It's a big summation. So when you go ahead and try to, now what you can do is, you can go ahead and plug in the ising. When you look at the ising model, remember? So when you go ahead and write out the ising model expression and evaluate this, and then plug it back into. So remember what we're trying to do is find this xs is equal to xs given xr is equal to xr for r less than s. That's what we're trying to evaluate. It turns out that if you just go through the calculations for this, plug in the ising model. In fact, in order to simplify your work, you can just take a finite number of values here and actually go through that calculation fully. What you will get finally is that this probability is only dependent on a certain set along the boundary. So it turns out that, let me just draw this again. I'm going to show the picture first. It turns out that the probability of a pixel being equal to s given all the past ones will depend upon the entire set of boundary pixels. So there are all these pixels along the boundary, and if we consider an infinite lattice, it turns out that this probability is not just dependent on a piece order window, a little window. In fact, it's dependent on all these. So this kind of makes the point that a 2D MRF, we have provided an example of a 2D MRF which is not a 2D Markov chain of order P. Okay, because we saw the ising model was P is equal to 1. It certainly is not leading to a Markov chain of order P or anything. In fact, it's dependent on all the boundary pixels. So this is of course this is a set R. Right, so that is R, this is the center pixel, and these are the pixels beyond it. You can kind of get the intuition of what's happening because your ising model is going to involve sums over these, along with a lot of other things which get cancelled. Okay, so this is something for you to work out, but I'm just saying that when you write out the expression for the ising model, the boundary pixels kind of stay, they remain in that expression. So, therefore, what we have really shown is that we have provided a 2D MRF which is not a 2D Markov chain. So just to summarize what we have seen so far, right? So we started out with a 2D Markov chain and of order P and showed that it is a 2D MRF of order 2P. We showed that a 2D MRF on the other hand need not be a Markov chain, right? That's what we have shown. And there's a Venn diagram showing this picture, and the professor kind of explained this last time. So here we have 2D Markov chains of order P, and we know that they are in the set of 2D Markov random fields of order 2p. Whereas 2D MRFs of order p need not be 2D Markov chains of order p. Whereas in the 1D case, we showed that they were both equivalent. So I guess the story this picture is trying to say is that when you have a 1D lattice or a a directed acyclic graph type of structure, you can use a Markov chain or an MRF, and it turns out in 1D a Markov chain, there are a lot of nice results derived and they're much easier to work with. Whereas when you go to a 2D lattice, so when you have a graph with loopy dependencies, in that case a Markov random field is more expressive than a 2D Markov chain. So the story here is that so Markov random fields in 2D are useful. When you have loopy dependencies, a 2D MRF is more expressive. Alright, so that kind of ends this discussion about 2D Markov chains and 2D Markov random fields. So the last topic of this chapter is doing parameter estimation. Now, one of the things that we've kind of not talked about is, we looked at the ising model, right? So we looked at the ising model, we said we can use it as a model for images, and it was given like this when you have some kind of click structure, right? So data is a parameter, right? So let's say you want to actually use this model. How do you set these values? How do you learn these values given some data? So in general, doing estimation of parameters, because let's say you want to write a code and you want to implement something, you need to know how to kind of set these values, right? Or given some instances of from this ising model, for example, you want to kind of estimate what the parameters are. So this section is going to give us some insight about two things. This is not very easy to do. So first we're going to see why is it difficult to do parameter estimation, and secondly we'll provide a couple of a couple of solutions to deal with those difficulties. So that's what this section is going to be about. Okay, so why is parameter estimation difficult? The reason parameter estimation for MRS is difficult is because of the nature of the partition function, right? So you have this Z over here, and this has a very complicated form. So just for emphasis, I'm going to write out. So this is a general Markov random field, right? This is a general Markov random field. So if I want to just write an expression for Z of theta, so Z is the partition function, okay, and theta is some parameter. Now in that example that we looked at, the theta was equal to the number theta, just one parameter. But you can have any number of parameters. So one thing that we know, okay, if I want to write an expression for Z in terms of U, can anyone tell me like a way I can do that?
Just be the integral.
That's correct. Exactly. So basically, if you want to write an expression out, you basically just say that over X belonging to some set, you just sum it up, integral if it's a density, or sum it up if it's a mass function, like many of the cases we're looking at. And that should be equal to 1, right? Because it's a valid mass function. So you just plug into the expression, what you really get is that Z of theta is equal to the sum over X belonging to omega of n, where omega is a set of values that a single pixel or a single random variable can take, and omega to the power n is just a kind of power set. So all possibilities for all the pixels put together. So it has this type of an expression. And why do you think evaluating this is difficult? So
the energy function can have all kinds of crazy forms, right? So for example, like one energy function you think of is like the non-Gaussian like functions that we talk about for like map estimation, like GGMRF, I'm sure is like really crazy.
That could be one reason, and we will see some examples maybe in the next chapter where the potential functions the energy functions are packed.
There are so many combinations of X.
Exactly. So if you take a binary image, okay, of 1 million pixels, there are 2 to the power 1 million terms for this summation. So it's really hard. So that's the main difficulty. The difficulty comes because it's an intractable sum. Alright? That's what makes the parameter estimation hard. Nevertheless, let's just go ahead and see what happens when you just want to do a parameter estimation. So in order to do a parameter estimation for this, right? So this is the PMF. If you want to do parameter max, you want to estimate theta. That's what you're trying to do. So one estimate of theta can be obtained by the maximum likelihood estimation, right? So by maximum likelihood estimation, you just find the value of theta that maximizes this probability mass function. So remember over here, let's say I think one way to think about it is, imagine you've been given an image, like a value of x, which is like a measurement of some sort. You've been given an image and you want to estimate what is the value of theta, given that the image came from that mass function. So what we'll do is the maximum likelihood estimate is simply the arg max over p of theta of p theta of x, right? That's you've been seeing that all the while. And another way, I can take that is the same as applying log, and that is the same as taking arg min and taking the negative log of p theta of x, right? That's just this maximum likelihood estimation. And in this case, what you really get is, you'll get that in order to find the optimal theta, if you just go ahead and plug in the value of the mass function from here, you'll get that this is simply equal to u theta of x plus the log of 0 theta. Right? So 0 theta is this nasty term, the partition function. So, given that this is the expression, so what we can do right now is, how do I find the minimum of this, assuming that all the terms are differentiable and that the ML estimate doesn't lie on any constraint, it's not a constraint optimization. What we do is just take the necessary condition is that you take the gradient, set it to 0, the gradient has to be 0 as the minimum, right? So you can do that, so you just take the gradient of this term, that over here. So in order to find the optimal theta, so what we'll do is just take the gradient and set it equal to 0. So what you'll get is essentially g theta hat by radius, right? Because log derivative, we can just work through this. This is not very hard to see. So given an x, the optimal theta should kind of satisfy this. Now, in order to, we can further go ahead and simplify. You want to get some insight. You want to solve this system of equations for theta, right? So what we can do here is, given that you have set the gradient to 0, put this aside. So I'm just going to. So one thing you can do then is go back to the original partition function. Right. You remember that we had the original form of the partition function over here, right? We're going to go up here, use this, and plug it into this expression. And take the gradient of this, and then plug it into this expression over here. Alright? So this is canting through some of the algebra over here. So take the definition of the partition function, apply the gradient to this operation, and that gives you this step over here. Alright? And what that essentially tells you is that you get some gradient of u of theta times 1 over z theta that comes from here, and you get some term over here. Alright? And what you essentially get when you solve that is this is simply the expected value of the gradient of this energy function. Okay. So let's just step back for a second and look at what this means. We're trying to solve for the optimal theta. The optimal theta is obtained by solving this system. So this is an observation x. You take the energy function, find the gradient. Now, assuming some value, the optimal value of theta has to be such that the gradient of this should be equal to the expected value of the gradient. So this is a random variable over here, right? So it's an expectation over the over this, and the corresponding density function is our T of x, which is an MRF distribution, right? It's 1 over z times the exponent of minus u theta of x. That's the expectation. The expectation is that. That's still not a very easy problem to solve. So now instead, if we still focus down on certain class of u, if your MRF comes from an exponential family, then if you recall what you've seen is that for an exponential family, you can write the u of theta in terms of a statistic times the parameter, right? A statistic essentially distills all the information down to a few numbers. It distills the information for parameter estimation. So for the special case, when u is equal to this, when you take the gradient with respect to theta on the left side, so you're going to take this particular form of u and plug it in over here. Alright, so what is the gradient of this T of x times theta with respect to theta? So yeah, that's correct. So this T of x, right? So on the left side, what you just get is that the gradient of this is just equal to T of x. And on the right side, you get that it's just the expected value of T of x. So T of x is a statistic. So the point is, the optimal theta is 1 that matches the measured value, right? So this is an observation. The measured value of the statistic to the expected value of that statistic. So you've got to adjust the distribution parameter such that the expected value is equal to this. But, this is not very easy to solve still, this type of an equation, because you have to take an expectation, right? So, one way of kind of working around it is to use something called stochastic sampling, which we're going to see in the next chapter. So instead of actually computing this expectation, you generate samples from your Markov random field, compute for each sample, compute the t, and just take a mean. Alright? So that's what this method gives. So it gives you a method for matching up these things. So you take your measured value, generate a bunch of samples, find the difference between the measured and the generated sample, and use that to update the theta value. So that is one way of doing parameter estimation. So it's very hard because you need to generate samples from your distribution. Are there any questions?
No.
Okay. However, having said that, there's no guarantees that that the convergence of doing something like this is stable. So it's not a very easy thing to do. Nevertheless, stochastic sampling, generating samples from an image, is not an easy problem. So it's also computationally expensive. We know how to do it, but it's computationally expensive. So this type of parameter estimation method can be computationally expensive. So what is the work around it? So one of the other things that people have looked at doing is that instead of doing maximum likelihood estimation for estimating the theta, they do something called pseudo likelihood. So in pseudo likelihood, instead of maximizing instead of looking at the likelihood, they define a new function called the pseudo likelihood function. So the pseudo likelihood is simply the product of the conditional density of a pixel given its neighbor. Alright? So this is equal to the density function of the Markov random field. So you take conditional densities and just take a product, and this is an MRF, a general MRF. Is this equal? No. Right. So it's a kind of, that's called pseudo likelihood. So it kind of gets rid of those loopy dependencies that are there. So this is, of course, as I said, so that's why it's not maybe like a precise type. I mean, this is precise, but it's not equal to this. Certainly is not equal to this. So the pseudo likelihood is just another cost function we're going to maximize with respect to theta. So if you go ahead and write the pseudo likelihood function, then what you get is that theta hat is, instead of maximize, you just maximize the pseudo likelihood, and it's a product over all these terms. So you just take log and get a sum. Okay, so it's a sum of the log of the conditional density of every pixel given its neighbor. Okay, so the point is now one of the subtleties that you have to be careful about is that in general the parameter theta is associated with the original Gibbs distribution, right? So you got to express, you can do this maximization, but you need to express this in terms of the original Gibbs distribution that we started out with. Because if I give you a set of conditional distribution and you simply multiply it, it need not really match any global behavior of the random field. In fact, it can be some it need not be anything consistent. So one of the things that we have to do is kind of express each of those conditional densities over here from the original Gibbs distribution. I'll explain what that means. Alright, so remember that we're looking at a Markov random field and it has some associated Gibbs distribution, right? So this is P of P theta of x is 1 over z times, and this is the potential function, and C is the set of all the x, right? So from this we can compute the conditional density function, right? It's not very hard to do from this, given that you have this Gibbs distribution. You can write it out and you can evaluate an expression. So you got to evaluate this expression and then plug it back into the pseudo likelihood maximization function, right? Which is over this. So you go back, evaluate this, plug it back, and then what you get is you still get a kind of nasty expression. So from the pseudo likelihood, the estimate of the parameter theta hat is given by the maximization of the sum over all the pixels of this expression. Now, I think, more than like going into the details which can work out, what has changed from the previous ML estimation to the pseudo likelihood estimation? What was difficult when we did the ML estimation? What is the big difficulty I said that occurs in parameter estimation?
Find across many x's.
Perfect. That's correct. So it was a nasty kind of, it was huge. You had like 2 to the power a million possible states. Whereas when you do the pseudo likelihood, that's not true. This is the sum over all the pixels. This is the set of clicks which contain a certain pixel, which contain the pixel n, which is just a few clicks. And in the denominator, you have a sum over all possible values of a single pixel. Alright? So it turns out that this pseudo likelihood, because it kind of doesn't take into account the loopy dependencies in the MRF, the resulting math turns out to be this way. Now, having said that, the question is this any good? Like, is this really like, is it really like a good parameter estimate of anything? Because, it's just some pseudo likelihood. And the answer to this is it's kind of. Now, at least it has one good property. And one of the good properties about this estimator is that it is a consistent estimate. So, what is the meaning of a consistent estimate? So, does anyone remember? It's fine because it's something before. The thing about consistent estimate, the proper definition is that a consistent estimate converges in probability to the true value, or in other words, as the number of samples increases. So the point intuitively is that your estimate improves the number of samples, and that's always a good thing to have, right? In an estimator. So this pseudo likelihood estimator has that nice property at least, and it's better than doing something completely ad hoc. So therefore, this is one kind of workaround that is used. Alright? So that concludes chapter 10. So let me just quickly summarize what we have seen so far in chapter 10, right? So we started off, the first thing we saw what is an MRF, right? We defined it. The next thing we saw was what is a Gibbs distribution, and we related both of these to the Hammersley-Clifford theorem. The next thing we saw in this chapter was, we saw that 1D Markov chains of order P are equal to 1D Markov random fields of order P. The next thing we saw is a special case of a 2D Markov random field called the ising model. Right? So we saw the ising model, and what is the cool property? The property was that the boundary pixels can affect the pixel at the center in the ising model. So there are correlations between the boundary and the center, which are not present in a 1D Markov chain. And the final two things we saw that 2D MRFs are indeed more expressive than 2D Markov chains. So in a 2D lattice, it is useful to have a 2D Markov random field. And finally, we concluded by really looking at a small issue about how do we estimate the parameter. of the 2D Markov random field. And that's all I have for today. Thank you.
Recording is stopped.